Okay, so now we get to Hubble, right? You know, after whom the telescope is named, right? And he's an interesting character. Let's just say he's colorful and determined and whatever. I believe that his mentor was Lowell of the Lowell Observatory in Flagstaff. Okay, um, he's using a 100-inch telescope. When we say 100-inch, we mean that's the diameter of the telescope. 100 inches, 8 feet is 96 inches, right? Okay, so this thing, you know, you can walk inside the thing, right? This is Mount Wilson, and this is before Los Angeles was super bright and polluted the sky with light. And he's looking at spiral nebula, which he knows are galaxies. Okay. Now, an interesting story there is that he brought these plates, these film plates, to Lowell, I believe, and he's looking there, and he can pick out individual stars. He even finds Cepheid stars, right? These are those variable stars whose brightness can be determined by the period of their variability, right? So if you can find a Cepheid variable, right, you can determine its absolute magnitude, right? And then you just use the absolute magnitude, apparent magnitude, and you can find the distance to the star, right? So he starts to look at these spiral nebulas. He picks out these Cepheids, and he measures the distance to the stars and the recession velocity of many, many galaxies. Now, the interesting story is that, of course, he brought some of this evidence to Lowell himself. Lowell looks at what he's doing. He's looking at these spiral nebulas, and he says, oh, there's no stars there. Of course, they're just clouds of gas, right? So that guy missed out on it, right? He discovers there's a relationship between the distance to a galaxy and the rate at which it moves away from us. Very simply, the farther it is away from us, the faster it recedes. This is distant from us, right? This is our distance in this direction. This is how fast it's going. It's got a zero intercept, right? This is the simplest thing. This is Hubble's law, right? Okay. And there it is, right? Velocity is Hubble's constant times the distance to a galaxy. Okay. And then we think that the Hubble constant is about 71 kilometers per second of recession velocity. That's what it means, right? Per megaparsec of distance, right? Remember, a parsec is a long, long way. This is millions of parsecs, right? So if you were to look at some object a million parsecs from us, it would be receding at 71 kilometers per second. If we went 2 million parsecs, 2 million megaparsecs, 2 million parsecs, right? 2 megaparsecs away, it would be receding at 142 kilometers per second, okay? That's how this works, right? Okay. So just don't forget that that's a megaparsec. That's a parsec times 10 to the sixth, right? Okay, so what does it mean that every galaxy is moving away from us? Well, okay, the universe is expanding, right? And I will show you the rubber band demo. It will be just amazing. You'll look at that rubber band and you go, oh my gosh, I get it now, okay? So the question is, are we in a unique place? Are we at the center of the universe? If everything's moving away from us, does that mean we're at the very center of the universe? A logical question, right? And no, it doesn't, right? Let's suppose we have a universe now, and then the universe after is slightly expanded, right? This is slightly bigger than this, right? If you pick a particular spot, like that's us, right? Okay? And you superimpose the expanded universe on us, everything is moving away from that dot. The people in that dot say everything's moving away from them. And by the way, the farther away they are, the farther they have moved away, right? So the Hubble law works there, right? Okay. Or if we pick another dot, right, and superimpose it, again, everything is moving away from that dot. And we pick that dot because this is so easy to do, right? Everything moves away from that dot. We can even pick one up in the corner, and everything will have moved away from that dot if we superimpose the expanded universe, right? So what this means is that the universe is expanding. Hubble discovered the expansion of the universe, which of course, foreshadowing, right? If you run time backwards, that means that the universe was once much smaller, and you can predict how old the universe is from this roughly, right? You can predict that the universe emerged from something that was very small. This is the Big Bang. So this was, suffice it to say, a fairly major discovery, right? Okay, so what is the distance we find? And this is one way you can figure out how far away something is, right? is you measure the redshift of it and use the redshift as a meter to figure it out, right? So I'm going to use our approximate formula for recession velocity. So our delta lambda is 17 nanometers, right? 497 minus 480, right? So I go 17 nanometers. The original one, right? This, when they say it's a 480 nanometer line, that means it's the original one, is 480 nanometers, right? And then that equals our recession velocity over. And then since we're dealing with kilometers per second, right? Okay, I'm going to use 3.00 times 10 to the 5th kilometers per second, right? And now I'm set. So let's go 17 divided by 480 times 3e5. And that is 1.0625 times 10 to the 4th kilometers per second, right? Okay, so now we're going to use the Hubble's constant, right? V is equal to Hubble's constant times the distance to something in megaparsecs, right? Okay, so therefore distance is just V divided by Hubble's constant, right? Is that right? I do believe it is, right? So that's going to be 1.0625 times 10 to the 4th kilometers per second, right? Divided by 71 kilometers per second per megaparsec, right? And if you look at the units, kilometers per second will cancel. You'll get 1 over megaparsecs. So, okay, so divide by 71, and I get 149.6 megaparsecs. And then the question is how many sig figs? I guess because we got down to 17 there, we have 2 sig figs. So it's 150 megaparsecs. Yay. Okay. Okay, so that's that one. And then you have one more example, right? And I got this right out of the IB test. It says estimate the age of the universe from the Hubble constant of 71. Estimate the age of the universe from the Hubble constant of, here we'll get rid of the A, there we go, it's gone now, of 71 kilometers per second per megaparsec, right? Well, what we could do here is we go, okay, time is distance divided by velocity, right? So if I'm here, right, and there's some object that's here that's some distance away from us, it must be that distance away from us because originally, if we talk about, you know, the Big Bang, right, in the origin of the universe, these two dots were in the same place. But because the universe has expanded, it's some distance d, it has been traveling at v equals hd for that time, right? Okay, so we go d divided by hd, which means that the age of the universe is roughly 1 divided by the Hubble constant, right? And then the question is how is it 1 divided by the Hubble constant, and how do we do that? I'll show you that, okay? So the age of the universe is 1 over the Hubble constant, right? So that's 1 divided by 71 kilometers per second per megaparsec, right? Right? Well, that just, we can put the megaparsecs up there, right? So we have 1 megaparsec divided by 71 kilometers per second. So the question is, how long does it take an object going 71 kilometers per second to go a megaparsec? And the answer is it's going to take a long time because a megaparsec is a hell of a long distance, right? Heck, I said heck. All right, so a megaparsec, let's convert megaparsecs into, I guess, kilometers, right? Okay, so 1 times 10 to the 6th parsecs, right? Okay, a parsec is 3.26 light years, right? So I guess I got to convert it to light years. So 3.26 light years for a parsec, right? Okay, and then I guess we got to turn it into meters, right? So let's see, and these are the conversions they give you in the data packet. So I'm sticking to those. Okay, so then I'm going to multiply by 9.46 times 10 to the 15th, and this is meters per light year. right? And then we got to turn it into kilometers. So I guess we got to divide by 1,000, right? So 1 kilometer divided by 1,000 meters, right? Okay, so our units are parsecs, go the way of the bison. Light years go away. Meters go away, and we're going to end up with kilometers. So I'm going to do all this on my calculator, right? Okay, so 1e6, that's a megaparsec, right? Times 3.26 times 9.46 e15 divided by 1,000. Okay, do we have that right? There it is. Okay, so I'm getting 3.08396 times 10 to the 19th kilometers, right? Okay, so now let's divide this out, right? So that's going to be 3.08396 E19 kilometers, right? Divided by 71 kilometers per second, right? Okay, so divided by 71. And I get 4.3436 times 10 to the 17th seconds, right? So that's the age of the universe in seconds. Okay, and then I'm going to divide that 4.3436 E17 divide by what? 365.2425. I'll just say 25, right? Divided by 24 divided by 3,600, right? So this is dividing by this. So we're going to figure out how many years there are, right? So divided by 365.25 divided by 24 divided by. Okay, we're trying to figure out how many years it is, right? And I get 13.76 billion years, right? Which isn't, we're not too far off actually, right? Assuming that it's had the same rate of expansion, which isn't true, right? We get about 13.76 billion. We think it's about 13.7 billion years, right? Okay, so all right, there you go. There's some more example problems. You probably don't need to do them, but wouldn't hurt.